So today we are going to begin our Unit 1, which is all about finding limits. Okay? So everything that we do in Unit 1 is going to involve limits. Okay? So a limit is the behavior of our function as x approaches some value. So what we're going to look at is what is happening to the y values as we approach an x value. Okay. That's a limit. Now, we're going to talk about limits in a lot of different ways. We're going to look at them numerically first, then we're going to look at them graphically, and then eventually, I think tomorrow, we're going to start looking at them algebraically. Okay? So let's first figure out, well, let's look at this example, okay? So here I have our function. F of x is x cubed minus 1 over x minus 1, and here is our graph. Okay, everyone see the graph? Okay. Here is a table of values. Okay? If I want, and this is how we're going to write it, if we want the limit as x approaches 1 of f of x, that's how we read it. The limit as x approaches 1 of f of x. That means we're looking at the y behavior as we approach x equals 1. So what I want you to do is I want you to look at this table. What's happening to our y values the closer we get to x equals 1? What are they getting close to? They're getting close to 3. Okay? Let's look at the graph. Here we have an open coordinate at x equals 1. Okay, so there's not a value there, not a problem. Okay? I kind of like to think of it as like riding a roller coaster. Okay, we ride a roller coaster on our graph from either side. Our y values get closer and closer to 3. So we say the limit as x approaches 1 of f of x is 3. Because as we get close to x is 1, our y values approach 3. So we're going to investigate this with some numbers. Okay. I want you to write this down right here. The limit, there should not be an equal sign there. So I need to get rid of that. So ignore that little red blob. The limit as x approaches 2 of x squared minus 3x plus 2 all over x minus 2. Okay, that's the function we're working with, and we're looking at the limit as x approaches 2. Okay, so I want everyone to get out their calculators. Okay, you guys are going to help me here. We're going to figure out what's happening numerically as we get close to 2. Okay. So pod 1, I want you to find me the coordinates when x is 1.75 of this function. Pod 2, I want you to plug in 1.9. Pod 3, 1.99. Pod 4, 1.999. Okay, so you're plugging those numbers into that function. We're going to see what's happening on our graph. Pod 5, 2.25. Sorry, you off. Pod 6, 2.1, and then I'll do the other two. Okay. Mm-hmm. You are getting ahead of me. We will be allowed to do that.
Yeah.
Keep that in mind. Pod 1, do you have a value? What? 0.75. Pod 2. Pod 3.
0.99.
Pod 4.
I did.
What'd you do? Okay, I'll come back. Pod 5. What'd you get for 2.25?
1.25.
Pod 6.
1.1.
I'll come back to you guys.
0.999.
Okay, so if we look at this table of values, the limit as x approaches 2 of this function, what are those y values approaching? 1. Okay, now if I sat there and I made you plug in all 8 of those values, would that be very efficient?
Yes. No.
That would not be efficient at all. Okay, this is not how we are going to evaluate limits. But I wanted to show you what's happening numerically. Our y values are going to approach a number. It's not always going to be a nice number, but I picked some examples where they have been nice. Okay. What's more important is what's happening graphically. So let's talk about this graph. Logan, tell me what you did with the equation.
I factored the top.
Okay, so Logan looked at our function and he factored the top to x minus 2 times x minus 1. And what happens? Our factors cancel and we're left with x minus 1. Because we had factors that canceled, what does that mean graphically about our function?
Ooh, I remember this.
Tell us.
No, I remember what it is. I just don't know what it's called. Doesn't it mean you have a hole in the graph? Yes.
It means you have a hole in the graph. So really we have this graph with a hole at x equals 2. So what does that line look like? We have a y-intercept of -1 and a slope of 1. However, at x equals 2, we have a hole. So there's that graph. Remember graphing things like that last year? Okay. Anytime we have factors that cancel in our rational function, we have a hole. So this is what we were left with. We have the line y equals x minus 1, but a hole at the factor that we canceled out. So let's write our roller coaster. As our x values get closer and closer to x equals 2, we're approaching which y value? That hole is at 1. Okay? There's not a point there, but that's okay because we're talking about the value that we're approaching. We are not at 1, but we're approaching 1. Do you understand the difference? Yes.
So does that mean like when we're doing this, that hole will always be at the point we're like looking for in the limit?
Not necessarily. And that's a good question because I might give you this graph, Larry, and I might ask you for the limit as x approaches 1 of f of x. And what would you tell me if I asked you that? 0. As we approach x is 1, our y value is approaching 0. We have a coordinate there, and that's awesome, okay? But it's still the same process. Cool.
So how do we find the 2.1? Because there's really no like distinction in the. Is there a question mark by 2.1? On the table?
Okay.
Graphically, how would we?
Oh, graphic. We would have to plug that in. Okay. We did the table so I could show you what's happening with the numbers. I kind of want you to forget that we did that because that's not an efficient way. But I wanted you to visually see what's happening with those numbers. Okay? Let's look at another graph. Okay. Draw the graph on your paper. Okay. You're going to see a lot of graphs where there are holes and then there are coordinates above or below that hole. Okay? So I'm going to talk about two different things here. Okay? First, I want to talk about the limit as x approaches 2. If we follow our curve and get closer and closer to x equals 2, what are our y values approaching? Josie? If we write on our function, we get closer and closer to 2, what are we approaching with our y values? It is 1. Okay? As we get close to x equals 2, our y values, they're saying constant, but our y values are approaching 1. Now, what if I ask you for f of 2? Cole, what would f of 2 equal? Okay. When I'm asking you to evaluate the function, that means where's the coordinate? So where's the coordinate for x equals 2? Right there at 0. Okay. So here's our limit. As we get close to 2, our function's approaching 1. However, our coordinate is at 0 for x equals 2. So the limit is what we're approaching. The coordinate is where the dot is. All right. It is important for us to understand when a limit cannot exist. Okay? So far, I've showed you like 3 different examples where we have evaluated a limit and gotten a numeric value. There are 3 situations where a limit will not exist. And it's important for you to know those. Okay? So, first one. Okay? A limit that fails to exist. The first time this happens is when f of x is approaching a different number from the right side than it's approaching from the left side. Okay? If you're approaching a different number from the right than you are from the left, then your limit will not exist. And I will show you a picture of what each of these look like. Okay? The second case, actually, let me just show you a picture of what this looks like right now. Oh, does this look familiar? Are you guys getting too young for me? No? You guys are getting too young for me? Mean Girls? Thank you. Okay. When a limit doesn't exist, we get to say it does not exist. Okay? So this is what it looks like when our right and left behavior will not be the same. If I ask you for the limit as x approaches 0 of this graph, do you notice as we approach 0, up here we're approaching 1, Up here, we're approaching -1. Since they are different, the limit does not exist. Every single one of you needs to draw this graph up here. Don't worry about like these little symbols right here. But absolute value of x over x, this is a graph that you need to know what it looks like. So everyone needs to draw it. And understand that the limit does not exist as x approaches 0. Why does this graph look the way that it does? Okay. Remember, absolute value is like a piecewise function. Half of it is y equals x. The other half is y equals -x. Okay. So when x is positive, we have x over x, which is 1. When x is negative, we have -x over x, which is -1. Okay, that's an important graph for you to know. You will see that limit again.
Did you write it? What?
Don't worry, I scribbled those out later. It was a graphic from the book where I don't use those symbols, but it was a nice graphic from the book that I wanted to use. Okay. All right. The second case where the limit does not exist is when our function is increasing or decreasing without bounds. Our function is increasing or decreasing without bounds. What do I mean by without bounds? What do I mean? Increasing or decreasing without bounds.
Well, we thought like that would approach like infinity or negative.
Ah. Like this. Okay. Our function, in this case, keeps rising towards infinity. So, the limit as x approaches 0, well, on both sides of 0, it's growing and growing and growing towards infinity. It does not exist. The limit as x approaches 0 does not exist. Even though they're going the same way, which we'll come back and talk about this, right now we're going to say that it doesn't exist. Later we will have a different way of describing it, but the limit does not exist because there is no bound. Okay? And the third case where a limit does not exist is when it's oscillating between two fixed values as we approach x. This is probably the case that we will see the least. And I'll show you a really cool picture of what it looks like. But it is the third case. Okay? I promise you that there will be a question sometime in Unit 1 on a quiz and or a test where I ask you, what are the 3 times that a limit fails to exist? And I would expect you to be able to, some way, in your own words, describe these 3 situations. Okay?
Picture.
Potentially, for sure, describing with words. Okay? So, what does this one look like? Kind of sounds weird. What does it mean to oscillate? Show me with your arms. What does it mean to oscillate? This is oscillating. Okay? You're like bouncing between 2 values. Okay? And what happens is we're bouncing quicker and quicker and quicker. Okay? So as we approach, we're looking at the limit as x approaches 0 of this sine of 1 over x. And you can see as we approach 0, we're oscillating faster and faster as we approach 0. There's no way of knowing what is going on there. Okay, there's no way of putting a number on that limit. Okay, so this does not exist. Okay, like I said, this is the case that you will see the least out of the three, but still important.
Oh, without that's the vertical. I think it would.
It would.
Yeah,
It would.
skinny line, right?
Yeah, I mean, there's enough of some slope where it's passing the vertical line test, but it's just getting crazy. Like if we zoom in, like super zoom in, it would pass it, but it's not pretty, is it? Okay, so we are going to practice looking at graphs and evaluating their limits. That's what's going to be the most important out of today. All right, so I'm going to put a graph up here, and I have 4 things that I want you to evaluate. Right now, I want you and your group to work together for 90 seconds on these problems. I want to hear some good conversation about these limits. 1, 2, 3, go.
Well,
Okay, I might give you longer than 90 seconds.
so like let's say first
Yesterday it was hot.
I mean, one versus that's kind of
Talk to each other. No. So, okay, so what's happening is from one side it approaches 1 and the other side it approaches like 3.5, right? Since those are not the same, what does that mean? Like as we approach 1, the left and the right hand side are different.
So as X approaches,
So it means
right here. So that's
the limit's not going to exist.
Oh, wait.
All right, part 3. What's the limit as x approaches 3? You know what? How about this? Can I change it to x approaches 4? That way we can be a little bit more certain.
the last one. Yeah, the last one's already X.
Dang it. So why do I have that? I don't know. Let's change it to this.
Just do like 6.
Let's change it to x approaches 0. Pod 3, what would that be? 3. Do you agree with pod 3? The answer is 3. Okay. Pod 2, what's the limit as x approaches 1? Why does it not exist? Okay, from the left and from the right, we're approaching 2 different values, which means the limit does not exist. Okay. Pod 6, f of 1. Why is it 2, Abram? What did you see up there that made you guess 2? You saw a black dot. That is exactly right. Wherever that coordinate is, that is the function's value. Okay? Let's see. Pod 1, the limit as x approaches 4. 2, is that what you said? The limit as x approaches 4 is 2. There's not a value there, not a big deal. We are approaching that open circle, which is at y is 2. Okay. Just look at this picture. Just look at this picture. And I want us to figure out where the limit would fail to exist. So like those 3 rules that I gave you, which one of those are present? So 60 seconds, you and your group write down as many as you can.
Fail to exist or do exist?
Okay, which ones do they exist for? We'll start there. And let's just look at any integer values. Okay, what integer values do the limits for sure exist for? Okay. Now I want you to discuss the ones that they don't exist for. Which ones do they not exist for? Pod 5, give me one x value where the limit would fail to exist.
X approaches 0.
As x approaches 0, because we're coming from 2 different directions. Pod 4, I can't remember who I picked on and not. Give me another one. -2. Okay, you could describe this as what? Approaching without a bound. Pod 1, anywhere else? 4. Here again, we're approaching 4 without bound. F of 4 exists, but the limit does not exist. Pod 2, does the limit exist at x equals 2? Yes. It would be like around 1/2, right? Okay. Questions on that picture up there? Okay. We're going to do a quick activity before I give you your homework.